In this section, we are going to discuss about short circuit ratio, that is SCR, and two reaction theory, that is the theory of salient pole synchronous machine. The topics covered in these sections are significance of short circuit ratio, that is SCR, two reaction theory of salient pole synchronous machine, and related phasor diagrams. So first of all, let's discuss about short circuit ratio. The short circuit ratio of a synchronous machine is defined as the ratio of field current required to generate rated voltage under open circuit condition to the field current required to circulate rated armature current under short circuit condition. So this is open circuit and short circuit characteristics of a typical synchronous machine. Here, open circuit characteristic indicate the variation of open circuit voltage with variation of field current, and short circuit characteristic is the graph between short circuit armature current with respect to variation of field current. So, short circuit ratio is the ratio of field current required to generate rated voltage under open circuit condition, that is OA from this graph. OA is taken as IF1 and OD is the field current required to circulate rated armature current under short circuit condition. Let us take that value as IF2. So SCR is equal to IF1 by IF2. So we know from this graph it is clear that IF1 is responsible to generate rated voltage and IF2 is responsible to circulate rated armature current. That is, field current required to circulate rated armature current under short circuit condition is responsible to generate this much drop under short circuit condition. The entire voltage is getting dropped across the synchronous impedance under short circuit condition. So based on that concept, we can say that SCR is equal to V rated by I into ZS. What is ZS? ZS is equal to RA plus JXS. Usually for all machine, the resistance value is very low. If we are neglecting resistance, armature resistance value, we can say that SCR is equal to V rated by I into XS. So when we are taking V rated in denominator part, this equation become 1 by I into XS by V rated. So what is I into XS? It is a voltage drop which is created by XS. So what is V rated? That is the base value. So when we are considering this denominator, this part indicate XS per unit. So we can say that SCR is inversely proportional to synchronous reactance, or SCR is equal to 1 by XS. So SCR is equal to 1 by XS per unit. We can derive the expression for SCR from these OCC and short circuit characteristic itself. Now let's derive the expression for SCR using these open circuit and short circuit characteristics. So from these characteristics, we can see two right angle triangle, that is right angle triangle OAB and right angle triangle ODE. So I am drawing that one separately here. Right angle triangle OAB and right angle triangle ODE. When we are looking to this figure, it is clear that these two right angle triangles are similar triangle. If we have a ratio OA by OD, which can be equated by means of this ratio, that is AB by DE. Why? Because these two triangles are similar triangle. That is the only concept required in order to derive the expression for SCR using these diagrams. From the graph, SCR is equal to the field current required to generate rated voltage under open circuit condition to the field current required to circulate rated armature current under short circuit condition. That is IF1 by IF2. IF1 is OA and IF2 is OD. Okay. Then let's consider two right angle triangle OAB and right angle triangle ODE. These two triangles are similar triangle. Then we know SCR is equal to the field current required to generate rated voltage under open circuit condition. So that current is OA, and the field current required to circulate rated armature current under short circuit condition is OD. So SCR is equal to OA by OD. So since these two triangles are similar triangle, we can say that SCR is equal to AB by D. Refreshing EMF method, in order to find out synchronous impedance, what we done? Corresponding to same excitation, what is the open circuit voltage and what is the short circuit current? That ratio gives synchronous impedance. So same concept we can utilize in order to find the expression for XS. So synchronous reactance XS is the ratio of open circuit voltage to the short circuit current for same field excitation. Corresponding to this OA, that is IF1, open circuit voltage is AC and short circuit current is AB. So XS is equal to AC by AB for same field current. We need to convert this synchronous reactance into per unit. How to convert actual reactance value into per unit? So per unit value is equal to actual value by base value. In this case, actual value of XS by base value of XS. So XS is equal to what is actual value? AC by AB. Then we need to divide that with base value. Okay, that gives XS per unit. Now let's see how to find out base reactance. Base reactance is rated voltage by rated current. What is rated voltage? Rated voltage is AC. This is the rated voltage. Then what is rated current? This is rated current DE. Okay. So rated voltage by rated current gives base reactance. Voltage by current gives impedance, that is reactance. In this case, we are assuming armature resistance as 0. So base reactance is equal to rated voltage by rated current, which is equal to AC by DE. Now we can substitute the base value in this equation. So XS per unit is equal to AC by AB into 1 by reactance, base reactance. So we need to multiply this with reciprocal of this one. Okay, so AC by AB into what is the reciprocal of this one? DE by AC. AC and AC we can cancel, and the final answer is XS per unit is equal to DE by AB. Now we can look into SCR. What is SCR? By using the similar triangle principle, SCR is equal to AB by D. Then what is the value of XS we got? XS we got it as the reciprocal of this one. So we can say that SCR of an alternator is reciprocal of per unit value of synchronous reactance. That is SCR is equal to 1 by XS per unit. So SCR value is having more importance in synchronous machine. Now let's see the importance of SCR in detail. SCR affects the performance, physical size and cost of the synchronous machine. First important point is voltage regulation. So we know SCR is equal to 1 by XS per unit. What is XS? Total reactance of the machine. XS is equal to XL plus XA. Usually the value of around 80 to 85% of the reactance is armature reaction reactance. That is due to armature reaction effect. So SCR can be approximated as 1 by XA. What is XA? XA is armature reaction, the fictitious reactance that represent armature reaction. So we can say that SCR is equal to 1 by armature reaction. As armature reaction is more, the reactance that represents armature reaction effect is also more. As armature reaction effect is more, synchronous impedance will be more. So as Zs is more, we know the equation for the terminal voltage as E0 minus I into Zs. As Zs is more, the deviation between V and E0 will be more. Okay, as Zs is more, V minus E0 or E0 minus V will be more. E0 minus V is more, voltage regulation will be more. So it indicates that as SCR is low, voltage regulation will be more. That means in order to maintain constant terminal voltage, we need to control the excitation, the field current need to be varied over wide range in order to maintain constant terminal voltage. That is the significance of SCR, how it relates to voltage regulation. So voltage regulation is directly proportional to armature reaction, that is inversely proportional to SCR. Voltage regulation is inversely proportional to SCR. Second point is size and cost of the machine. We know SCR is equal to 1 by XS per unit, which is approximately equal to 1 by XA, that is fictitious reactance that represents armature reaction effect. And also we have seen that SCR is proportional to 1 by armature reaction. What is armature reaction? Effect of armature flux on distribution of main flux. So as armature reaction is more, armature MMF or armature flux will be more. That is, armature reaction is proportional to armature MMF or armature flux. What is armature flux? Armature flux is equal to MMF by reluctance is equal to N into I by reluctance. So we can say that armature flux is inversely proportional to reluctance. Armature reaction and armature fluxes are inversely proportional to reluctance. So as reluctance increases, flux will decreases. As flux is decreasing, armature reaction is decreasing. So as reluctance increases, flux will decrease, armature reaction reactance will decrease. As reluctance increases, flux decreases and vice versa. We know air gap length is directly proportional to reluctance. As air gap length is increasing, reluctance of the magnetic path is increasing. By considering this part, that is armature reaction is proportional to armature flux, which is proportional to 1 by reluctance, we can say that which is proportional to 1 by air gap length. From this we can conclude that armature reaction is inversely proportional to reluctance, that is armature reaction is inversely proportional to air gap length. So as armature reaction is inversely proportional to SCR, so which is proportional to 1 by air gap, so SCR is proportional to air gap length. So as air gap length is more, the size of the machine will increase. As the size of the machine increases, the cost of the machine increases. So SCR is directly proportional to cost and size of the machine. So from here it is conclude that thus machine with the higher value of SCR is having more air gap length and it requires higher field EMF to generate same value of induced EMF E0. Thus field winding become bulk and hence field pole length has to be increased. Thus high value of SCR increases size, weight and cost of the synchronous machine. So SCR is directly proportional to size and cost of the machine. So next point is output power. The power developed by the synchronous machine is given by P is equal to 3 E0V by Xs into sine delta. Okay. So from here it is clear that power is inversely proportional to Xs. If power is inversely proportional to Xs, power is directly proportional to SCR. Okay. So what is Pmax here? Pmax is equal to 3 E0V by X. Pmax is inversely proportional to Xs and Pmax is directly proportional to SCR. So the power developed by synchronous machine is directly proportional to SCR. Next point is synchronizing power or stability factor. What is synchronizing power? The derivative of P with respect to delta is known as synchronizing power or stability factor. That is, it is the rate at which power developed by the machine varies with respect to change in delta, and this measures the degree of stability of the machine. So Psy is equal to dP by d delta, which is equal to 3E0V by Xs into cos delta. So from here it is clear that synchronizing power is directly proportional to 1 by Xs, or Psy is directly proportional to SCR. So synchronizing power developed by synchronous machine is directly proportional to short circuit ratio. So machine with low SCR develop less synchronizing power. Machine with high SCR develop high synchronizing power. So synchronizing power is coming into picture when we are considering parallel operation of the machine. Due to any reason, if one of the machine is going out of synchronism in parallel operated condition, in order to bring back that machine into synchronism, some synchronizing power is required. That synchronizing power is Psy. So in order to increase synchronizing power, in order to bring back the machines in synchronism due to sudden disturbance, so we need to give more synchronizing power. So if the machine is having more SCR, obviously synchronizing power will be more. So we can say that stability of the machine is directly proportional to synchronizing power. So we know synchronizing power is inversely proportional to Xs. That is, synchronizing power is directly proportional to short circuit ratio. And also we know short circuit ratio is directly proportional to air gap length. So altogether, we can say that stability of the machine is directly proportional to air gap length. If air gap length is more, the stability of the machine becomes more. Let's see that one in detail. So to increase the stability of the machine, air gap length need to be increased based on this. So if air gap length is more, obviously the reluctance is more. If reluctance is more, wide range of field excitation is possible without saturating the machine. So if air gap length is more, reluctance is more, so we can increase field current over wide range without saturating the machine. Thus, wide range of voltage control is possible. So if air gap length is less, what happens? If air gap length is less, the machine gets saturated fast. We can't obtain good control of voltage over wide range. If air gap length is more, there is more scope of over excitation, which ensures strong locking between rotor and stator pole, which in turn increases the stability of the machine. If the locking between the stator and rotor poles are strong, the stability of the machine is more. So we can say that stability of the machine can be increased by increasing air gap length. So SCR is directly proportional to stability of the machine, which is directly proportional to air gap length of the machine. Coming to the fifth point, that is short circuit current. Current is inversely proportional to synchronous impedance. That is, current is inversely proportional to synchronous reactance. That means current is directly proportional to short circuit ratio. That means smaller value of SCR gives smaller value of short circuit current due to large value of synchronous reactance. If SCR is less, synchronous impedance will be more, synchronous reactance will be more, therefore current is less. Now let's see the summary of significance of short circuit ratio. First of all, let's consider low value of SCR. Low value of SCR gives higher value of Xs, which results large variation of voltage with load. Therefore, voltage regulation will be more. So, low value of SCR gives more voltage regulation. Then, second point is to maintain constant terminal voltage, field current need to be vary over wide range. Then third point is low value of SCR means low value of synchronizing power. That is, SCR is directly proportional to synchronizing power and which is directly proportional to stability limit. So low value of SCR means low value of synchronizing power and consequently lower stability limit. Then lower value of SCR results low value of armature short circuit current. Why? Because current is directly proportional to SCR. Then coming to a high value of SCR, high value of SCR gives lower value of excess, which results low variation in voltage with load. Therefore, voltage regulation will be less. High value of SCR gives lesser voltage regulation. Then, to maintain constant terminal voltage, field current need to vary shorter range. Then, high value of SCR means high value of synchronizing power and consequently a higher stability limit. High value of SCR results high value of armature short circuit current, and it also affects the size and cost of the machine. So from here it is concluded that armature reaction and voltage regulation are inversely proportional to short circuit ratio. Air gap length, size of the machine, cost of the machine, output power of the machine, synchronous power coefficient, stability limits, all are directly proportional to short circuit ratio. Typical value of SCR for cylindrical rotor synchronous machine lies in between 0.6 and 0.9. And for salient pole machine, the typical value of SCR lies in this range, that is 0.9 to 1.5. And the typical value of SCR for synchronous condenser is 0.4. What is synchronous condenser? Synchronous condenser is an overexcited synchronous motor working under no load condition. In the case of synchronous machine, we can control the power factor by controlling the field excitation. If the synchronous machine is overexcited, it gives the characteristics of pure capacitor. The value of SCR for synchronous condenser is usually 0.4. So this completes the discussion of short circuit ratio. Next, let's see two reaction theory. So before discussing two reaction theory, let us refresh the important concepts which we got from SCR discussion. So we know armature reaction is directly proportional to armature MMF or armature flux. As armature current increases, armature flux increases. Therefore, armature reaction also increases. So we know armature flux is equal to MMF by reluctance, which is equal to Ni by reluctance. So as reluctance increases, what happens? Armature flux will decrease. That is, armature reaction is decreasing. So armature reaction is inversely proportional to reluctance. As reluctance increases, flux decreases, and vice versa. We know air gap length is directly proportional to reluctance. So as air gap length is increasing, reluctance is increasing. As reluctance is increasing, armature flux is decreasing. Thereby armature reaction is decreasing. So armature reaction is inversely proportional to air gap length. Therefore, the reactance that represents armature reaction is inversely proportional to air gap length. So as air gap length is less, reactance will be more. As air gap length is more, reactance will be less. So this is the important concept which is required during the discussion of two reaction theory. Now let's see the construction of cylindrical rotor synchronous machine. So this is rotor of the cylindrical rotor synchronous machine, and this is the stator of cylindrical rotor synchronous machine. Here we can see that air gap between stator and rotor is uniform. As air gap is uniform, as we discussed, if air gas is uniform, only one reactance is sufficient to represent armature reaction. So in cylindrical rotor synchronous machine, as air gap length is uniform, single reactance is sufficient to represent the effect of armature reaction. But in the case of salient pole machine, air gap length is not uniform. Here air gap length is less In this area, air gap length is more. So in salient pole machine, there are two axes, namely direct axis, that is D axis, and quadrature axis, that is Q axis. What is direct axis? The axis of the peeled pole, or the axis passing through the center of the peeled pole, is known as direct axis or D axis. So this is direct axis, which is represented in red color. Then axis which is midway between two D axis is known as quadrature axis. That is the axis which is quadrature to two adjacent D axis, or the axis passing through the center of two adjacent D axis is known as quadrature axis, or simply Q axis. So blue line indicate Q axis. Along D axis, air gap length is small, and along Q axis, air gap length is maximum. So as air gap length is not uniform, here we need two reactances to represent the effect of armature reaction. That is one along direct axis and another along quadrature axis. So along D axis, air gap length is minimum. If air gap length is minimum, reluctance is minimum. If reluctance is minimum, flux will be more. If flux is more, armature reaction will be more. If armature reaction is more, XA that represents armature reaction effect is more. If XA is more, synchronous reactance will be more. So along direct axis, synchronous reactance will be more. But along Q axis, air gap is more, therefore reluctance is more, therefore flux is less. If flux is less, armature reaction is less. If armature reaction is less, synchronous reactance is less. So along direct axis, we can have maximum reactance, maximum synchronous reactance, and along quadrature axis, there is less synchronous reactance. Thus, along D axis, armature reaction is more, and along Q axis, armature reaction is less. Thus, XAD is more than XAQ. So the reactance that represents armature reaction effect along D axis, that is XAD, is more than the reactance that represents armature reaction under quadrature axis, that is XAQ. So in salient pole machine, as air gap length is non-uniform, two reactances are required to represent the effect of armature reaction. So this is the basic concept of two reaction theory. Let's discuss all these things in detail. Now let's see different diagrams related to salient pole and cylindrical rotor synchronous machine. So this is the stator part and this is the rotor part. Here we can see there are large number of projecting poles, and if the machine is having large number of projecting pole, that machine is salient pole type. So this is one D axis, this is another D axis. So along D axis, direct axis, air gap length is minimum. Along quadrature axis, air gap length is maximum. This is the rotor of a two-pole salient pole alternator. So this is the direct axis and this is the quadrature axis. Along direct axis, air gap length is minimum. Along quadrature axis, air gap length is maximum. This is the actual structure of salient pole rotor. This is the damper winding and this is the field winding. Then this is the stator and this is salient pole rotor. In cylindrical rotor alternator, large number of slots are provided on the rotor periphery to accommodate field winding. Usually 2/3 of this rotor periphery is having slot and 1/3 portion is not having slot. So whenever the field windings are energized, the unslotted portion become poles. So this is the rotor structure of cylindrical rotor alternator. This is the actual structure. Now let's see the theory of salient pole synchronous machine in detail. This is a 4-pole salient pole alternator. Here blue line indicates D axis, direct axis, and this orange line indicate quadrature axis. Direct axis and quadrature axis are there in salient pole synchronous machine. So correspondingly, there is maximum flux linkages along direct axis, minimum flux linkages along quadrature axis. If flux is more, direct axis reactance is more, and in quadrature axis flux is less, therefore reactance is. So direct axis synchronous reactance is represented by XD, and quadrature axis synchronous reactance is represented by XQ in the case of synchronous machine. So we know, as we discussed, in salient pole machine air gap length is not uniform. Air gap length is small along polar axis or direct axis. Air gap length is maximum along quadrature axis, that is Q axis. Because of the variation of air gap length, there will be variation in reluctance of the magnetic path. More air gap possess high reluctance and less air gap possess less reluctance. Why? Because air gap length and reluctance are directly proportional. So polar axis and quadrature axis provide low reluctance and high reluctance respectively. So along polar axis, that is direct axis, air gap length is minimum, therefore reluctance is minimum. Along quadrature axis, air gap length is maximum, therefore reluctance is maximum. Therefore, armature conductors in direct axis is having maximum flux linkages compared to the conductors which is placed along quadrature axis. As we know, inductance is, what is inductance? Inductance is flux linkage per unit current. As flux is more, inductance will be more. As inductance is more, inductive reactance will be more. Omega L gives inductive reactance. So along direct axis, inductive reactance is more. Along quadrature axis, inductive reactance is less. Therefore, inductance along direct axis is maximum compared to inductance along quadrature axis. Thus, armature reaction reactance along direct axis, that is XAD, will be more with respect to armature reactance along quadrature axis. So armature reaction reactance along direct axis is represented by XAD, and armature reaction reactance along quadrature axis is represented by XAQ. The total reactance of the machine along direct axis, that is the synchronous reactance along direct axis. So XD is equal to XL plus XAD, and the synchronous reactance along quadrature axis, that is SQ, is equal to leakage reactance plus armature reaction reactance that represents armature reaction along quadrature axis, where XL is the leakage reactance per phase. XAD is the armature reaction reactance along direct axis, which is the fictitious reactance to represent armature reaction effect along direct axis. XAQ is armature reaction reactance along Q axis, that is the fictitious reactance that represents armature reaction along quadrature axis. The value of SQ is less than XD. Usually SQ will be around 60 to 70% of XD, direct axis reactance. It is to be noted that in non-salient pole machine, that is cylindrical rotor synchronous machine, direct axis synchronous reactance and quadrature axis synchronous reactance are equal. That is, only one reactance is there in non-salient pole alternator. Why? Because the reluctance of the air gap length is uniform in cylindrical rotor alternator. In cylindrical rotor alternator, air gap length is almost uniform. Therefore, XD is equal to SQ. But in salient pole machine, air gap length is not uniform. It is varying between XD and SQ. The difference between XD and SQ is known as saliency. So saliency is 0 in cylindrical rotor machine, and saliency is XD minus SQ in the case of salient pole machine. Now let's see the theory of a salient pole synchronous machine with the help of a two-pole salient pole alternator. This is the direct axis, that is the axis passing through the center of the pole. The axis which is midway between these two poles is quadrature axis. The flux is maximum along direct axis. Due to this flux, EMF is induced in stator conductors, that is E0. This E0 is lagging flux by 90 degree. If alternator is loaded, armature current will flow through armature conductors, and let this current is lagging behind E0 by an internal power factor angle psi. Now, according to two reaction theory, this armature current is resolved into two components. One is along direct axis, that is represented by ID. That ID is in quadrature with E0. And another component is in phase with the quadrature axis, that is in phase with E0. So this armature current is resolved into two components. One is along direct axis, that is ID, and this ID is quadrature with E0. The angle between E0 and ID is 90 degree. And another component of this armature current is IQ, that is in phase with both Q axis and E0. As we know, if we are considering E0 and ID, this ID is lagging E0 by 90 degree. As we are considering E0 and ID is responsible for complete demagnetization effect of armature reaction. If we are considering IQ and E0, both are in phase. So the power factor of operation when we are considering E0 and IQ is unity power factor. What is the effect of armature reaction under unity power factor? The effect of armature reaction under unity power factor condition is cross magnetization. So IQ is responsible for cross magnetization effect of armature reaction, and ID is responsible for demagnetization effect of armature reaction in this case. So ID may be either demagnetization or direct magnetization depending on this current. If this current is coming in this direction, ID is leading E0 by 90 degree. So under that condition, magnetization effect will come into picture. So this is the basic concept of two reaction theory. Armature current can be resolved into two components, that is ID and IQ. Due to this ID, magnetization or demagnetization will come, and due to this IQ, cross magnetization will come into picture. So now let's see this part alone as phasor diagram. So this is E0. And this is armature current, which is lagging E0 by an internal power factor on this side. So according to two reaction theory, I can be resolved into horizontal component which is in phase with E0, which is responsible for cross magnetization effect of armature reaction, and this is the vertical component which is in quadrature with E0 and in phase with the direct axis, which is responsible for demagnetization effect of armature reaction in this particular case. Why? Because ID is lagging E0 by 90 degree. So what is Blondel two reaction theory? So this is the statement of Blondel's two reaction theory. According to this theory, armature reaction MMF is resolved into two components. One is magnetizing MMF. It may be direct magnetization or demagnetization according to this current vector. If current is lagging E0, this is demagnetization effect. If this current is leading E0, magnetizing MMF will be direct magnetization, as we discussed earlier. Then another component of this armature reaction MMF is cross magnetization MMF. The same statement can be represented in terms of current also. According to Blondel's two reaction theory, armature current can be resolved into two components. First component is a component of armature current which is in phase with induced EMF E0, that is in phase with the quadrature axis. Therefore, that component of current is represented by IQ. And another component is a component of armature current which is in quadrature with induced EMF. This is the vertical component which is in quadrature with E0, and this component is in phase with direct axis. Therefore, it is denoted by ID. The angle between E0 and I is psi. So IQ is equal to I cos psi. And this vertical component is equal to I sin psi. That is IQ is equal to I cos psi and ID is equal to I sin psi. This is very important. Let I be the armature current and psi be the angle between E0 and I as shown in figure. This current I can be split into two components, namely in phase component, which is in phase with E0, that may be represented by horizontal component, and another component is ID, which is in quadrature with E0, that is termed as vertical component. In short, the in phase component of armature current, which is in phase with E0, which is in phase with the quadrature axis IQ, that is obtained as I cos psi, produces cross magnetizing effect of armature reaction, that is cross magnetizing MMF. So when we are considering E0 and I, this power factor is unity power factor. Under unity power factor, the effect of armature reaction is cross magnetization effect. Then second component, the quadrature component of armature current, which is quadrature with E0 and which is in phase with the direct axis, that is ID is equal to I sin psi, produces magnetizing effect. It may be either demagnetization if current is lagging E0, may be direct magnetization if current is leading E0. Under zero power factor lagging condition, effect of armature reaction is complete demagnetization. Armature reaction effect is direct magnetization under zero power factor leading case. Let AD be the direct or demagnetization component of armature EMF and AQ be the cross magnetization component of armature EMF. Then AD and AQ can be represented by corresponding component of armature current, that is ID and IQ. Both these component of armature reaction EMF rotates at synchronous speed with respect to armature winding, and each of them may be looked upon as due to a set of fictitious poles. The set of poles producing direct magnetization or demagnetization effect of armature reaction can be marked as ND and SD, and these poles are in alignment with main pole. The set of poles producing direct or demagnetization effect that depends on power factor of operation. For zero power factor lagging, the effect is completely demagnetization. For zero power factor leading operation, effect is completely demagnetization. Therefore, demagnetization or direct magnetization effect of armature reaction can be marked as a fictitious poles ND and SD. It is either increasing or decreasing the net flux. Another set of poles producing cross magnetization effect of armature reaction can be marked as NQ and SQ, and these poles are midway between two main poles or midway between ND and SD. The magnetic circuit associated with AD, that is ND and SD, the fictitious poles ND and SD, is same as that of the main magnetic circuit, while the magnetic circuit associated with AQ, that is NQ and SQ, is made of large path of airspace between the main pole. These are the main poles, north pole and south pole. This is the direct axis, the axis passing through the center of the field pole, the axis which is midway between two D axis or two adjacent pole, that is quadrature axis. Then this is the main MMF, the MMF or flux produced by means of main pole. Armature current is lagging behind E0 by an internal power factor angle psi. Under this condition, current is split into two components. One is vertical component, that is ID, and another one is horizontal component, that is IQ, which is in phase with E0. So ID is responsible for demagnetization. Due to ID, some MMF AD is produced. So AD can be generated by means of two fictitious poles, that is ND and SD. The magnetic circuit associated with AD is same as that of the main magnetic circuit. Internal power factor of operation when we are considering ID is zero power factor lagging. Under zero power factor lagging, the effect of armature reaction is complete demagnetization. So a demagnetization MMF is generated due to ID. Here the effect of ID is demagnetization. So under north pole SD will come, under main pole south pole, ND will come due to this demagnetization effect. The internal power factor of operation considering IQ and E0 is unity power factor. Under unity power factor, cross magnetization will come into picture. Due to IQ, that is I cosine, cross magnetizing MMF is generated. So this cross magnetizing MMF, that is AQ, is assumed to be generated by means of fictitious poles NQ and SQ, which are lies along quadrature axis. So this is the cross magnetizing MMF which is produced by IQ cosine. So at any instant, the net flux is the sum of main MMF, demagnetizing MMF, and cross magnetizing MMF. Now let's see the Phasor diagram of alternator considering two reaction theory. Here ED is the armature reaction voltage drops along direct axis, and EQ is the armature reaction voltage drops along quadrature axis. Here let's consider lagging power factor condition. Armature current is lagging E0 by an internal power factor angle psi. And this current is split into two components. One is vertical component, that is ID, which is in phase with the direct axis, and another component is in phase with the E0, which is in phase with quadrature axis. IQ is equal to I cosine and ID is equal to I sin psi. So since this current is lagging, the magnetization component of armature reaction shown in figure is demagnetization. Why? Because ID is lagging E0 by 90 degree. The power factor of operation is 0 power factor lagging. Under 0 power factor lagging, armature reaction is having complete demagnetization. The demagnetization component of armature reaction MMF, that is AD, is assumed to be produced due to some imaginary pole as discussed earlier, ND and SD, which are in alignment with the main pole and moves along with them. Let E0 be the induced EMF without any armature reaction, that is the induced EMF due to main pole, and ED be the induced EMF due to fictitious pole ND and XD, that is the voltage drop due to armature reaction along direct axis. Assuming the current is lagging, then due to demagnetization, ED is in opposition with E0. Thus, net induced EMF EM is equal to E0 minus ED. The cross magnetizing component of armature MMF, that is AQ, is assumed to be produced by an equivalent fictitious poles NQ and SQ, which are midway between main pole. Now let's consider the voltage drop due to armature reaction along quadrature axis. Let EQ be the induced EMF in armature winding due to fictitious poles NQ and SQ, which is in quadrature with E0 and lagging behind E0. So EQ represents the voltage drop due to armature reaction along quadrature axis, which is leading IQ by 90 degree. So it comes in quadrature with E0. So in order to get a clear idea about the Phasor diagram of alternator considering two reaction theory, it is to be noted that ED, that is voltage drops along direct axis due to armature reaction, which leads respective current, that is ID, by 90 degree. So the resultant of E0 and ED gives EM. Then EQ, the voltage drop due to armature reaction along quadrature axis, that leads respective current, that is IQ, by 90 degree. Here we can have the vector EM. Then we need to subtract EQ from EM in order to obtain internal induced EMF EA. This Phasor diagram is based on Blondel's two reaction theory, considering ED and EQ are the induced EMF due to fictitious poles ND-SD and NQ-SQ. Here let's consider lagging power factor case. Armature current is lagging E0 by an internal power factor angle psi. This armature current is splitted into two components. One is along E0 and another one is in quadrature with E0. The in-phase component of E0, that is IQ, is in phase with the quadrature axis, and quadrature component of armature current, which is quadrature with E0, that is ID, is in phase with direct axis. Since ID is lagging E0 by 90 degree, ID will generate a demagnetization MMF AD. And according to this theory, this demagnetization MMF is assumed to be generated by means of a fictitious poles ND and SD. Due to demagnetization, the induced EMF ED, that is the voltage drop due to armature reaction along direct axis, ED is leading ID by 90 degree. Therefore, net induced EMF EM is E0 vector minus ED vector. Then we need to consider the induced EMF due to a set of fictitious poles NQ and SQ. EQ is leading IQ by 90 degree. Now, the resultant of E0, ED and EQ phasor gives the internal induced EMF EA. So from this EA phasor, we need to subtract leakage reactance drop. Leakage reactance drop is leading I by 90 degree. Then we need to consider armature resistance drop, which is to be drawn in parallel to armature current. Now we considered armature resistance drop, leakage reactance drop, the voltage induces due to armature reaction. This resultant gives terminal voltage. So from this phasor diagram, it is clear that the vector V plus I into RA phasor plus I into XL phasor plus EQ phasor plus ED phasor gives no load induced EMF E0. Angle between E0 and I is psi, and angle between E0 and V is load angle or power angle delta, and angle between V and I is the power factor angle phi. So in general, if we are considering lagging power factor condition, under that condition demagnetization and cross magnetization will come into picture. The resultant induced EMF in alternator, that is internal induced EMF, is the vector sum of EM and EQ. To obtain terminal voltage, we need to subtract all voltage drop phasors, that is leakage reactance drop and armature resistance drop, geometrically from EA phasor. So we can conclude that terminal voltage is the vector difference between E0 minus ED and EQ phasor minus IXL drop minus I into RA phasor. So this is the phasor diagram of a salient pole alternator considering EQ and ED as the induced EMF due to a set of fictitious poles. Now let's discuss the phasor diagram of salient pole alternator considering EQ and ED as voltage drops. That is, EQ is equal to IQSQ and ED is equal to IDXD. In order to draw the phasor diagram, it is to be noted that ED leads ID by 90 degree. That is, ED is equal to IDXD leads respective current ID by 90 degree. EQ, which is equal to IQSQ, which leads IQ by 90 degree. And this phasor diagram is based on Blondel's two reaction theory considering ED and EQ as voltage drops, and all drops are adding with terminal voltage. Let V be the terminal voltage and armature current I is lagging voltage by the power factor angle phi. It is required to add all voltage drops with the terminal voltage in order to obtain the induced EMF in alternator. Armature current I is lagging voltage by the power factor angle phi. First of all, let's resolve armature current into two components. One is horizontal component, which is horizontal to induced EMF, that is IQ, and another one is quadrature component, which is quadrature to E0, that is in phase with the direct axis. So ID is the quadrature component of armature current, which is quadrature with E0. So we don't know about sign. So anyway, let's mark ID as I sin psi. After completing the phasor diagram only, we can obtain the value of psi. And IQ is in phase component of armature current, which is in phase with E0 and which is in phase with the quadrature axis, which is equal to I cosine. Then from the tip of voltage phasor, we need to draw a line or phasor. Length should be very small as armature resistance is small. From the tip of voltage phasor, we need to draw a phasor which is parallel to current phasor, that represent I into RA phasor. Then from the tip of I into RA phasor, draw a line or phasor at an angle 90 degree in anti-clockwise direction. That is, from the tip of I into RA phasor, we need to draw a phasor which is leading I by 90 degree. That represents I into XL phasor. Now, the resultant of V, I into RA and I into XL gives internal induced EMF in armature, that is EA. Now, from the tip of EA phasor, that is I into XL phasor, we need to draw a line at an angle 90 degree, that is in anti-clockwise direction, and which is leading IQ by 90 degree, that is IQ SQ, that is EQ. Then from the tip of EQ, we need to draw a line which is leading ID by 90 degree, that gives ED. Now the final phasor represents E0. Angle between E0 and V is load angle delta, and angle between E0 and I is internal power factor angle psi. So in short, the two reaction concept of salient pole machine replace the effect of armature reaction by two fictitious drops ID x AD and IQ x AQ. What is XAD? Armature reaction reactance along direct axis and armature reaction reactance along quadrature axis respectively, where ID and IQ are component of armature current along direct and quadrature axis. Each of these component of current, that is ID and IQ, produces leakage reactance drop. Here it is assumed that leakage reactance is same for both component of current. The synchronous reactance along direct and quadrature axis are represented as XD is equal to XL plus XAD, which is known as direct axis synchronous reactance per phase, and XQ, which is equal to XL plus XAQ, which is known as quadrature axis synchronous reactance per phase. The voltage equation based on this modified two reaction concept is as follows. Terminal voltage is E0 minus I into RA drops minus IDXD minus IQSQ. Here XD and SQ include leakage reactance. So this is the voltage equation considering modified two reaction concept. Based on this voltage equation, we can draw the phasor diagram. Let V be the terminal voltage and I be the armature current, which is lagging voltage by power factor angle phi. It is required to add all voltage drop with the terminal voltage in order to obtain the induced EMF in alternator E0. So armature current is lagging voltage by the power factor angle phi. Now we can resolve this armature current into horizontal, that is IQ, and vertical component ID. So ID is equal to I sin psi and IQ is equal to I cos psi. Psi will obtain only after completing the phasor diagram. Then we need to add all the drops. First of all, let's add armature resistance drop. Armature resistance drop I into RA is drawn from the tip of V phasor, which is parallel to armature current. So this is I into RA phasor. Then let's consider IQ SQ phasor. So from the tip of I into RA phasor, we need to draw a phasor which is leading IQ by 90 degree. Then from the tip of IQ SQ phasor, we need to draw a phasor which is leading ID by 90 degree. That phasor is IDXD. Now the final phasor diagram is E0. That is vector sum of voltage phasor, I into RA phasor, IQSQ plus IDXD phasor gives no load induced EMF E0. Angle between E0 and V is load angle or power angle delta. Angle between E0 and I is internal power factor angle psi. So this completes the phasor diagram of salient pole alternator considering modified two reaction theory.